Well, a warm welcome, everyone. Thank you for joining. We're done with the trig unit from this Calc prep assignment. It is now time to start combining skills together. We're going to be combining topics, and from this point forward, you're really going to get a taste of what it's like to see word problems which need to be carefully analyzed. Okay, so we're going to need to use verbal analysis and some geometry formulas in this one so that we can interpret what exactly is being asked and how to answer the question mathematically. So, without further ado, this is Math from the Void. Math coming at you pretty much out of nowhere. Let's get started. You should have a notebook, pencil, or a pen, whatever you choose to write with is totally fine. And let's look at this problem. We have a manufacturer that wants to design an open box having a square base, okay, that's kind of important, and a surface area of 108 square inches, okay? So they're giving us how much surface area is on this open box with a square base. Let's first kind of draw the situation so we know what's going on. We have this kind of a square down here. And then we have some kind of a height. And the box is open. Wow, that was pretty bad at the end there. I think this needs to go higher, that's why. Yeah, that looks a little better. This box is open, so we're not using any material for the top. So this like top side, there's nothing covering that. We just have the four walls and the bottom, which is a square base. So let's label that as a square would be with the same side lengths. And here's our H for the box. We're limited in how much material we have. That's the surface area. But how do we formulate the surface area here? Well, the surface area is going to be composed of four walls, which is 4 times xh. That's the area of any one of these like side walls, like that one, or this one, or the two in the back. Plus, we have x squared. Okay? This is going to give us the surface area, and we're told that this composes 108 square inches. Now let's read the question. What dimensions, like meaning the length, the side of the base, and the height, will produce a box with a maximum volume? So we want to maximize the volume given the limited amount of surface area that we have here. You're going to have to get used to doing this in calculus. We can use this constraint to sort of isolate one of the variables, in this case h. Let's solve for h. So we'll have 4xh equals 108 minus x squared. Then we just divide by 4x. Everything divided by 4x. So now we have that h equals 108 minus x squared over 4x. Okay, so what I want to do here actually is I want to take the 1/4 out, and that's going to leave us with 108 over x, because we're still dividing by x, minus just x, because x squared over x is just x. So then we're going to use this height into the volume formula. We're going to have v equals x times, x squared times 1/4 quantity. This is going to get a little messy. I'm going to pull the 1/4 out. Let's get the 1/4 out front and just multiply the x squared into these guys. So that'll give us 108x, right? Because x squared multiplied in cancels an x, leaves another x, minus x cubed. And this is a cubic, which we can't really find the maximum of a cubic algebraically, not until calculus anyways. So what we're going to have to do here is we're going to take a look at the numerical analysis. We're going to use a table of values. We're going to plug in some different x values, and see what happens to the volume by basically just evaluating a function. So you can do this by hand, but it's not that pleasant. You can do it by hand and with a calculator. It's still not really that pleasant to write them all down and just plug in values. I think it's better to use a function in a table, much like what you have on DESMOS. So I actually have the function plugged into DESMOS for some values, and we'll see what it looks like. So I encourage you to use DESMOS. DESMOS is a great tool. But just a second, be patient with me, and I'll post this onto the board. Here is a table of different x values and the volume of the box that it produces. Remember that this is v of x. So what do we notice? We notice that x, if it's 0, the volume is 0. No surprise. But as x increases, we see that the volume is also increasing. But what do we catch here? So it's 103, and then it's back to like 103. In fact, it's lower. It's 103.25. So what happened? It must have been going up and then started going down. And it's looking like x equals 6 is producing a significantly high volume, like a maximum volume of 108. Notice that it continues going down from there. So if x gets too big, that means that this is going to be a really, really, really wide base, but we're not going to have any material left for the walls. So the walls are just going to be like these little, it's going to look like a little ghetto wrestling ring. I don't know. There's going to be no volume there. Like, we're going to start decreasing the volume because making the x larger is flattening the box. So we want x to be in the sweet spot where it's kind of big, gives us a nice base area, therefore a nice volume, but it's not too big so that we don't have any more material for the walls. We need enough material for the walls to make them tall. Now you might ask me, what about, 5.3 or something? How do we know that 6 actually produces this nice value? It's a pretty nicely written problem. The number 108 is kind of a nice number, but let's just investigate that question a little bit further. Let's see what happens really close to 6, like before 6 and after 6, and you'll see that x equals 6 is a reasonable significant value that produces a maximum volume. See that? So when x equals 5.9, when we haven't yet gotten to x equals 6, the volume of the box is just under 108. And then once we have x get larger than 6, like 6.04, that's not even that much larger than 6, then the volume again drops below 108. So that is proof enough that x equals 6 gives us a really, really nice value, 108 there. Which means that the x value is 6, and the height is, remember the formula for that? We used it, right? We used it to substitute. 108 minus x squared over 4x. So this is going to be 108 minus 36 over 24. It's a pretty quick calculation. 72 hours divided by 24 hours a day. It's 3 days. All right, so these are the dimensions that we can comfortably say would produce a maximum volume. Now, you'll have to wait until calculus to actually find the maximum. It gives you something to look forward to, though. Let's move on to the next problem. What is the radius of a cylindrical soda can? So, cylinder, you're going to have to recall the cylinder formula, with a volume of 512 cubic inches that will use the minimum material. So they word things like this. They're going to start wording problems in this way, where it's not exactly clear what they want us to do here. So minimum material, what does that mean? I kind of hinted at it last time. I mentioned it in a way a few times. We're talking about surface area. Because the surface area represents like the amount of stuff. Like it might start as a flat sheet of metal and it gets like bent and folded and rolled or whatever it is. And so that's the amount of metal that would be used. We want to minimize that amount of metal. So we can call this S. And how would we represent this? Let's take a look at a cylinder, but of course a cylinder is a circle, basically. with a height. I mean, you guys have seen soda cans, soup can, or whatever, toilet paper roll. These kinds of things are basically cylinders. And we have the radius there, and we have the height which goes up. Makes a right angle with the ground. That's our height. I guess I could have also just put it here. And so the material that we need to use is basically the two circles times 2. And this is the radius. So what's the amount of area that we have there? Think about that. And then what about the amount of area surface on the outside, like around it? Like if we were trying to wrap it with a label, it would go around it. That's gonna, if we snip it and roll it out, sort of flatten it out, it basically just makes a rectangle, right? You can imagine that the rectangle like fits perfectly around the circumference. And that's a key word there, circumference, because the length of this rectangle is literally circumference, because it needs to go and wrap around the circle one full time, which is what the circumference is. It's going around the circle once. And there's a formula for it, 2 pi r. So you got to recall some of these geometry formulas. It's honestly kind of disappointing when I hear a lot of students worry about, oh, are they going to give us the volume formulas or the geometry formulas? You guys should know these. And even if it's not crystal clear right now, by the time you're in calculus, you need to have those crystal clear. They need to be solid. Because you can get a situation about any given shape. And don't just rely on them giving you formulas. Assume that they're not going to give you formulas. All right, that's a little bit of lecture. Sorry to get testy. So this is the surface area. We have one of these surfaces that goes around the circumference of the can. And then we have the top and bottom of the can, which are just 2 identical circles. So that means that the surface area S is equals to pi r squared times 2, because there's 2 of those circles, plus 2 pi r times h. And we are told that we have a specific volume of 512 cubic inches. So how do we represent the volume? Just like in the box, the volume of what's called a uniform solid, which means it's the same shape all the way up, is just base area times height. So it's basically just a circle that's like going up. If you were to 3D print this, you would have like the circle part, and it would just like be doing, layers of circle the whole way up. So we have pi r squared. This cylinder is much uglier than the other one, actually. We have pi r squared times h. That is our volume. Okay, now we have a value for that, though. We have that pi r squared h equals 512. So we can again use this principle of substitution to take our condition, our restricted condition of 512 cubic inches, and try to somehow figure out how to minimize this. Maybe we should solve for h. See what I mean? We're going to divide both sides of this constraint equation by pi r squared. Sorry, if that doesn't look like an equal sign, I don't blame you. Because it doesn't look like an equal sign. That looks more like an equal sign. This is going to be 512 over pi r squared. Beautiful. And we can use that now for our surface area. Remember the equation? I hope you do. You should be actively recalling these things and try to memorize these things. So we have 2 pi r squared plus 2 pi r times h, which is going to be this 512 over pi r squared. All right, we can simplify that for sure. Look at this. We have pi r, so we end up with 2 pi r squared plus 2 times 512 is 1024, and that's divided by r. Okay, let's see. So again, we're going to get this into DESMOS. I think it's a great idea to use DESMOS as a tool. And I'm just going to represent this equation on our table. You'll see on the function. So 2 pi r squared, and I'm just going to use x because why not? Plus 1024 over x. Let's get it on a table, and we'll have 0. We'll have 0 to 9. And what we're representing, again, here it is the amount of surface area given the value of the radius r. I put x in the DESMOS, but so of course we can't have 0. That wouldn't make any sense because it wouldn't have a volume of 512 cubic inches. If we made the radius 1, this would be how much surface area is required, how much material is required. So we see that that's probably not a great idea, but it is going down as our radius increases. And it seems to reach sort of a lowest point here at 4, but that doesn't perfectly look like the lowest value because we have some decimals here. So maybe we'll want to check some values that are near 4, like 3.8 and 4.1. Sure enough, you guys take a look here. We see that 4.1 produces a lower surface area than 4, which means we can continue increasing the radius little by little. So let's see if we try 4.16. We're doing a numerical analysis because we're trying to zoom in closer and closer to the exact radius that's going to give us the lowest amount of surface area. So 354.88 is our lowest so far. See if you can find a good amount that's lower than all the others. And it just takes fiddling with DESMOS a little bit. Let's see, at 4.3 it's still going down. Let's see, 4.34. 4.34 seems to be the lowest. I'm sure you guys can find something even lower if you get a little bit more specific. But for me, this is what I'm getting. And of course, we can solve these things with calculus. So once we get to the level of calculus, we'll get an exact answer. But it seems to be that the radius is approximately 4.34. And there's likely going to be a root involved or something like that, which causes this. If this is the radius, let's remember what is the height of this can. It's going to be 512 divided by pi r squared. And we're going to get an approximate value of that. Again, we can just use DESMOS really quick. Let's plug that in. 512 divided by pi times 4.34, or whatever value you used. If you found a better value for r, feel free to use that. I'm just going to use r equals 4.34 because that seems like a reasonable one that I got. And apparently that's going to be, oh, this is suspenseful. Where is it? Okay, 8.6524 approximately. And these are all in inches because I believe these were given in inches, yeah, cubic inches. Okay, let me make sure it's asking about the dimensions. Oh, it's just asking about the radius actually. So I didn't even need to find the height. I should have read the problem more carefully. That's all they were asking for. Great. All right, let's finish things up. I feel like I'm eating up some of your guys' time here. Okay, the last one we have here is finding the area of an equilateral triangle with a side length of x. Okay, so an equilateral triangle, you'll remember, is a triangle with all equal sides, and at the same time, it has all the same angles, which makes sense because the amount that an angle is, like how far open this is, kind of dictates how long this will be, right? That controls, how long it is here. If it were a smaller angle, like for that angle, notice it wouldn't be as long of a side. So we have all equal angles here, meaning what? meaning that they are all 60 degrees, because we know that the interior angles of a triangle have to add up to 60 degrees. So if we have a side length x, and it's an equilateral triangle, these are all x, and all of the angles are 60 degrees. Now we want to try to find the area of this. We can do something clever, and this is going to rely on geometry. We can split this down the middle. I'll draw it a little bit better. We can split this down the middle to form a right triangle, because in order to find the area of a triangle, we typically want to use just 1/2 base times height. There are other methods, but we want to use 1/2 base times height. And by splitting this triangle down the middle, we have created a convenient 30, 60, 90 right triangle. Notice that by splitting it down the middle, it's cutting the angle in half of 30 degrees now. So the full thing would be 60, but we've cut it in half. And this now is x over 2 rather than x, because the whole side length is x. And since that whole side length is x, this entire length is x. And that works with the proportion of a 30, 60, 90 triangle. Remember that the short side should be half of the hypotenuse for a 30, 60, 90 triangle. If that wasn't sharp in your mind already, go back and review both your 30, 60, 90 triangles and your 45, 45. Okay, so how can we find the height then of this? Well, we know that the height, we use Pythag theorem, but you should also just remember that the long side needs to be √3 times the short side. So we can call this √3 over 2x. And if that's the height of this split triangle, it's also the height of the full triangle, like before we split it. Therefore, the area is simply 1/2 base, which is the full x, because we want the area of the entire equilateral triangle, times the height, which is √3 over 2x. So all in all, we get √3 over 4 x squared, and that can be a convenient thing to know. If you want to know how much area there is, maybe you're using tiles, right? Maybe you have tiles and they're equilateral tiles. If you literally want to know how much surface area the tiles take up, you can use this formula. It's very easy. You just measure one side of the tile, and then assuming that all the sides are truly the same, that it's actually equilateral, you can just multiply by how many tiles you have, and then you can multiply by cost or whatever it is. Now, some useful things when we're formulating these word problems, using verbal analysis, geometry skills, calling back to polynomial situations, and also employing technology when it's useful. It is pretty useful to use technology. I'm not going to say that technology is useless. It does speed up our output as educators. Like if I had more visual 3D models, it'd be very easy to demonstrate some of these things. I can show you a cube I can show you a box that's increasing in x and simultaneously decreasing in h, or whatever it might be. But DESMOS is great, and I do want you to have the mental hardware to be able to calculate things, plug numbers in, and that makes more room for you to understand the concepts once you get to calculus, which is a comprehensive subject. We're going to incorporate lots of different topics, everything you've learned up to this point. It's starting to come together. Yeah, I think you can tell I'm pretty excited about this. So that should do it. Enough blab out of me. I'll see you guys next time.